So now we're going to look at the equation of a circle in the coordinate plane. And we'll start with a special case where the circle is centered at the origin, so the point 0, 0. And then we'll do the case where it's centered elsewhere. This is just really an application of the distance formula, or really we could just take it all the way back to Pythagoras, because what's the definition? Let's see. So specifically, we're going to look for the equation of the circle centered at the origin with radius 5, and then we'll generalize. And the key is that the definition is the set of all points with distance to the origin equal to 5. Okay, well, first, how do we say all points? Well, we're going to describe that with variables. We're going to say the point has coordinates x, y. I've got an example. If x was 4 and y was 3, not coincidentally, that looks pretty familiar, then the distance would be 5. In general, we're going to be looking for an equation in x and y. And this is going to be so fundamental to a lot of stuff we do next semester as well, graphing and thinking about relations between variables. So we got an equation in 2 variables. It's not a totally new thing, that says that this distance equals 5. Okay, and that's really not that hard. The distance between x, y, and 0, 0, we just break out the distance formula. So it's exactly like that previous video with the distance formula. We're just plugging in the case where one of the points happens to be 0. And instead of saying, oh, I'm going to take a random point and I'm going to calculate this distance and it's going to be new information for me, I'm just going to set that equal to 5. Now, we don't like square roots that much, so we actually kind of go back and say, you know what, Pythagoras in its most basic form, this is really Pythagoras in its most basic form for the triangle where this is equal to x, this is equal to y, and this is equal to the radius. Here, that's going to be 5. And so we get x squared plus y squared is the radius squared. So note, this is an easy mistake to make. Note that the 25 is the square of the radius here. But the same story is true in general. I lost my little bullet points. The general equation for a circle of radius r centered at the origin is x squared plus y squared equals r squared. Sometimes we even look at the very special case of r equals 1. That turns out to be very, very useful to focus on. That's going to be x squared plus y squared equals 1. So for right now, we're interested in a little bit more generality, but I wanted to mention that. So again, let's go back to this picture and just see, what does this mean geometrically? Right, I wanted to animate it. We've got all these different points x, y. Maybe some of them are really special numbers like 3 and 4. But no matter where I go on that circle, I should be able to count on, oh, here's 3 and 4 again. And I want to make a point actually about the signs in a second. But wherever I go on that circle, I should be looking at a right triangle. If I look at the x coordinate of that point, that's exactly just saying, how do I get horizontally from the origin to the right x location? And the y coordinate is how much do I have to go up or down to get to xy? And always, those form a right triangle with hypotenuse 5, and this is really just saying, giving that information. X squared plus y squared equals 25. In general, x squared plus y squared equals r squared. One thing I want to point out is that this is a little bit new in terms of right triangles. This is not so unfamiliar. Notice there's no negative numbers. X and y are both positive coordinates here. And so everything is positive. But if I go into another quadrant, and we'll be doing this a lot, reviewing a lot of our coordinate geometry and how it fits with all kinds of stuff. Here's a place where x is minus 4.4 and y is plus 2.37. Or here, they're both negative. Now here I'm asking the computer to measure the lengths, and they don't have the minus signs. But if I actually look at the x and y coordinates, they can totally be negative. They're both positive up here. They're both negative down here in the third quadrant. Here x is negative, y is positive, and here x is positive and y is negative. Those are all legal. You need to be able to describe all 4 quadrants of the circle. And the nice thing is that as soon as you do these squares that show up in the formula, those minus signs go away. That's very similar to what I was saying with distance along a line with the absolute values. Here, the squares do that job of erasing any negative information. But you want to make sure you know that x and y themselves can be negative numbers. They are coordinates, not just lengths. So we'll make sure to pay attention to that. Let me upgrade the picture. All right, new picture. The center is now not at the origin. I want the center to be 3, 1. And our notation we're almost always going to use for that when we want letters to go in a master formula to denote the coordinates of the center of the circle. We're going to use h, k. I like to think, you can think h is for horizontal. That's the horizontal coordinate of the center. And k turns out to be just a convenient letter that's near that in the alphabet. So you can think of it as standing for vertical if there was a silent K in front of vertical. So this is the coordinates of the center. Here it's going to be 3, 1 in the example that I'm showing. And I'd like to know, what is the equation that's satisfied by x and y here? If I've got a point and I know to be on that circle, I know the condition is that it's got to be exactly 4 units away from the center, which is now 3, 1. Well, that's just exactly saying if I calculate the distance between this variable point xy and this fixed point hk, I should get 4. So again, I just use the distance formula. Equivalently, I'm writing down Pythagoras for the triangle that I'm showing you right there. And the key thing, new thing, just like in the distance formula video, those legs of the triangle, like this horizontal leg, is the difference of the x coordinates. Here, the 6.03 and the 3, the difference of that is 3.03. That's one of the legs. Here, the difference, 3.61 minus 1, 2.61, that's one of the legs. Those have to match in Pythagoras with the 4. So what are we getting here? In this case, x minus 3 squared plus y minus 1 squared. That's the squared distance to the origin. That should be the square of the required distance, which is the radius of the circle. So it's very similar to what we were seeing here. Here it was just plain x squared plus y squared equals the radius squared. Here it's a modification, but that's exactly like what you see in the distance formula. So this is exactly a calculation of the squared distance between a variable point that we're testing to see if it is on the circle and the fixed point 3, 1. And then we're saying what I care about is that that should be equal to the square of the given radius. So in general, we're just going to make everything a letter. If h and k are the coordinates of the center, usually you think of that as fixed, and x and y as variable, and r is the given radius. So usually, even though it's a general formula, in a lot of particular applications, just like in this example, h and k are probably going to be known a lot of the time. For more sophisticated problems, maybe not. R is probably going to be known, and then it's going to be an equation that lets x and y be variable and describes all the different possible variable points, all the coordinate pairs for x and y that would satisfy that equation. So one last thing, let's look at a problem like problem number 2 a bit in the book. Find the equation of the circle with center 2, 4 that passes through the point 5, 5. So I'm giving you the center. So that's a lot of it. So we can plug stuff into slots partly. I know that by definition that h is just the x coordinate of the center, k is the y coordinate of the center. So part of it is just literally plugging things into this template. But the problem is that r is unknown. But it's not hard to find. You know, that probably needs another end. Okay, so let me actually draw that circle. GeoGebra is pretty good at that. Okay, I want the equation of that circle. And the key is that it's not hard to find R because here's the center. Here's a point on the circle. Hey, let's use the distance formula for that one known point. That will give me R. And then that will tell me how to describe a random point that's on the circle. So I'm going to be able to figure out an equation for all these random points by using the fact that I know that point is on there. Okay, so the solution, not the evolution, is that R is just the distance from between those two known points. And that's 5 minus 2 squared plus 5 minus 4 squared square root of 9 plus 1. That's root 10. So the radius very, very often, like we're familiar with Pythagoras, it might end up being something with a root. Of course, the nice fact is that the equation involves R squared, so it's actually going to still be relatively pretty. So it's just going to be the quantity x minus 2 squared plus the quantity y minus 4 squared is equal to 10. And that's going to be the equation that specifies where all these other points could be on the circle.